If you're anything like me, you're fascinated by the current state of artificial intelligence and the research surrounding it. However, the tempo at which things are moving might seem a bit too hard to follow, and it seems like there's new improvements in the field every 5 seconds. That's exactly why I think it's crucial to understand the fundamentals first. These foundational concepts serve as the backbone for all the innovation we see today. That's what makes this simple project so exciting to me, and I hope it will be for you too. It's pretty quick, easy, and I hope you will like it. In this video, I'm assuming you already know the basic syntax of C++ and have a solid foundation in math. That means familiarity with basic C++ libraries, algorithms, programming logic, and an understanding of calculus fundamentals. You don't necessarily need prior knowledge of machine learning, because this project is perhaps the simplest machine learning gets. I think that makes it an excellent starting point for beginners and anybody interested in some basic machine learning. The problem we're tackling might seem simple to us. Imagine a function with given x values of 1, 2, 3, and so forth that map to y values 1, 3, 5, and 7. What's the value of y when x is equal to 5? Well, to us, the answer is obvious. It's 9. But how do you teach a computer to figure this out? You could of course hardcode the function, but what if you wanted the same program to work for a different sequence of numbers or a different function? This is where linear regression comes into play. Given the x and y values for some function f of x, where f is a linear function, we want our program to predict the value of y for any given x. Alright, so let's start with the first function. Let's make a function that predicts the y values given the x values, the slope, and the y-intercept of the function. We simply just create a variable to store the predictions and iterate through the given x values, multiplying them by m and add b onto them. Store the value we get into predictions, and finally return the predictions. Next on the list is the mean squared function. It computes a measure giving us an idea of how far off our predictions are from the true values. It calculates the square difference for each point, sums them up, and divides by the total number of points. It's really quite simple, and it helps just to show how wrong our predictions are. Okay, we have these two functions, but however, this is still hard-coded. We have a vector of our points x on which we perform the operation dependent on m and b and check how close our predictions were, but the point of our program is to predict those values m and b. To make the program adjust itself, we use gradient descent. Gradient descent adjusts m and b to minimize the error using calculus-based optimization. For each data point, it calculates the gradients or how much m and b need to change, and it updates them using a learning rate. The learning rate is really basically just a number that tells our gradient descent function how fast we want it to change. A big learning rate means faster change, and a small one means slower and more gradual. In practice, it tends to be on the smaller side. It's also important to know how we got the gradient itself. For that, it's necessary to take the derivative of our loss function. In our case, that's the mean squared error. Let's see how the code looks. We make a void function since we won't be returning anything. We take in the m and b values, the learning rate, and x and y values. We define the m and b gradients, and we get the size of our x data. Now come the derivatives we just found. To find them, we can use a loop, get our current predictions, and calculate the gradients by first summing up the initial terms. Finally, we change the m and b values according to the gradients by finally calculating the gradient by dividing everything by the size of the data, and of course applying our learning rate. Alright, so finally now in the code, we have the predict function, the mean squared error, the gradient descent, all the standard stuff that we talked about already, and we have the main function in which we initialized the data set, the parameters. As you can see, we have the epochs here. We will train for 10,000 steps with a learning rate of 0.01, which is a relatively small learning rate, although it is usually smaller. Of course, we initialized the parameters to be 0 and 0 just for the sake of it being easy. And of course, here we train the model. So as you can see, we loop through the epochs, check the error. Depending on the error, we move the gradient descent stuff. And of course, we want to see how it works. So it will print progress every 10 epochs here. That's a little mistake. And of course, finally, we will want to test the model. So let's see how it works. Okay, so we run it. And now in the debug console, as you can see, it's actually very accurate, but that is because the data is very simple and it's linear, so there's really no margin for error. An interesting thing would be to actually lower the epochs. So let's see what happens when we lower them. Okay. Yeah, as you can see, it's a bit less accurate. So essentially, we overfitted the data, and it works here because we were talking about a linear function. All right, so I suggest you guys play around with these values a bit and see what happens. It's usually pretty fun to see if you put a big learning rate, what happens. The entire model usually explodes, or if you put an epoch that is too small, it's going to be very inaccurate. If it's too big, it's going to be way too accurate for the data, and then it just kind of doesn't work for anything else. And that's it. I want to leave you now with a few questions that could spark your curiosity that you will see on the screen now. I also want to thank you for watching, and I sincerely hope you learned something.